Formolab 2 was about investigating resistive forces, and just a little intro is that during this lab we're trying to see how the viscosity of a fluid impacts the terminal velocity of a falling object, and the goal is to compare the terminal velocities of a falling object in dish soap compared to the terminal velocities of a falling object in water. We are predicting that the dish soap solution would have a higher resistive force since it is more viscous than water. In this lab, our main findings were that the data could not be obtained for a water trial. No terminal velocity was reached due to a lack of sufficient volume. But however, the dish soap trial showed a terminal velocity of 0.25 meters per second. For our models, our system schema, the ball is the only thing within our system, but however, there is also fluid, the cylinder, and the earth, which have contact with each other, and the earth has gravitational effect on everything. Our energy pie charts, we start with just potential energy before the ball is moving, and then as it is falling, it is decreasing in potential energy, building up kinetic energy, and also building up internal energy. And then when the ball hits the bottom of the cylinder, the circle is smaller because internal energy was lost due to friction, and there's only kinetic energy because potential energy is gone. Our force body diagram has a normal force of the ball on Earth pointing up, and that is the N3 pair of the force of gravity of Earth on the ball going down. And also there is a viscous force or a resistive force from the fluid on the ball that is pointing upward. Our experimental design was we used two graduated cylinders that were each filled with different liquids. The first one was water and the second was dish soap. The metal ball bearings were dropped into each of the cylinders, and then the velocity was determined using the tracker software on our computers to further perform our calculations. Our independent variable was the type of liquid because we changed that throughout. Our dependent variable was the velocity, and our constants was the height in which the ball was dropped. The ball was dropped from 9 inches both times, and the amount of liquid was always 40 milliliters, and the mass of the ball and radius remained constant as well.
The experimental setups and the velocity graphs are shown for both trials. The velocity for the water experiment was 1.53 meters per second, and for dish soap it was 0.25 meters per second, showing the velocity was faster for water due to the dish soap having a greater viscosity. This makes sense as when viscosity increases, the intermolecular forces of the substance also increase, which would decrease the velocity. We know the soap trial reached terminal velocity as the velocity graph plateaus, so it would have zero acceleration. Terminal velocity, however, was not able to be calculated for the trial with water as not enough data points were present when using tracker software. We would have been able to determine terminal velocity if we used a larger volume of water for the metal ball to fall through. However, there is still an increase in velocity of the ball in water due to gravity, and the resistive forces cause the acceleration to slow down eventually, which can be seen in the velocity graph as it goes constant or levels off. We focused on viscosity for this lab, not drag. Terminal velocity depends on the size, shape, and mass of the falling object. Once terminal velocity is reached, forces equal each other, meaning the viscosity or the resistive force is equal to the force of gravity. We were able to calculate the terminal velocity by multiplying the ball's mass by gravity. From here, we were able to use the viscosity equation to solve for mu, which is the proportionality constant. This was relevant to solve for as this value represents the viscosity of the fluid. Sample calculations are shown, and the proportionality constant for dish soap was greater than that for water, which makes sense as the dish soap is more viscous and therefore would have more resistance, which would match our prediction.
When looking at the resistive force tested in our experiment, we compared the components of microscopic and macroscopic friction that affected the ball as it was falling into the liquid. We found that the substances used in each trial had varying degrees of friction, while the objects in the system were the same in each trial. This is similar to macroscopic friction. Microscopic friction, on the other hand, occurs when rough edges are rubbed against each other when in contact with the surface. The other main difference we found was that the friction was surrounding the entire object instead of friction only being present on the bottom of the object. The main limitation from our experiment was the lack of trials that we conducted. We only did one trial for the water and the dish soap, so it would have made our assumptions more concrete if we had conducted more trials. Additionally, we could have tested more liquids to better determine the relationship between viscosity and velocity because we only tested the relationship between the dish soap and the water. Also, the ball was not dropped from the top of the liquid during the trial, so that means the ball had time to gain velocity from the time it was dropped before it reached the water, and this means that the initial velocity would not be exactly zero, which could have affected our data. And then finally, we talked about in the data slide how the terminal velocity couldn't be reached because we didn't have a large enough volume of water for the water trial, and that resulted in Tracker not being able to give us enough data points to collect the terminal velocity for that trial.